The rest of section 8.1 is more for looking at the types of problems that you can solve once you understand the sampling distributions, and it usually only uses technology that we've already seen. So a lot of what we'll do with the sampling distribution uses the normal distribution, but we just adjust the standard deviation. So I want to go through a few problems to show you what types of problems you'll see with the sampling distribution in this chapter. So this one says a group of biologists was determined or has determined that the size of fish taken out of a pond has a normal distribution with a mean 10.2 inches, standard deviation of 1.4 inches. And the first part here says, what's the probability that a single trout taken at random from the pond is between 8 and 12 inches long? Okay, so this actually is just a normal distribution, and we're taking a single trout, so it would actually be like a problem that we saw in chapter 7. We plug in the mean of 10.2, the standard deviation of 1.4, and we have two limits, 8 to 12, and that will give us a probability. So I'll show you how to do that. Quick, I have the normal distribution open already. I'm plugging in the mean 10.2, standard deviation 1.4, lower limit 8, upper limit 12, and I'm getting a probability of 8.8427. Okay, now that's something we've done before, but now the second part of this question is asking what's the mean length x bar of 5 trout taken at random in between 8 and 12 inches. Now the mean is going to stay the same. .2, but the standard deviation needs to be adjusted. We're going to take that 1.4 and divide by the square root of the sample size, which in this case is 5. This 5 here, that's the square root of n from this formula up here. Okay, we make that adjustment to the standard deviation, and we put in those limits. And once we do that, it will give us the probability. Now, just conceptually think about this. In this part, a single trout was taken out. In this part, 5 trout were taken out. Do we think the chances of it being between 8 and 12 will go up compared to a single trout? Well, you kind of have to look at where the middle is. This 10.2 is right in the middle. And if we're making a smaller standard deviation, it's all getting closer to that center. That center is included in these limits here. And so we would think the probability is going to go up. Now, just intuitively, chances you get one thing that's far away from the mean versus getting 5 things that are far away from the mean, it's more unlikely, or it's more likely that you would get something really far away from that with the single trout versus 5 of them. Maybe the first trout's a little smaller, but then the next one may be a little bigger than the average. They even out. So like this larger sample size, we think this probability is going to go up. Now, when we do the calculation, I want to show you how to do this in Excel as well, just to save some time from going one device to another. If you want to do that 1.4 divided by the square root of 5, do the equal sign, then 1.4 the /, there's a built-in function for the square root. It's sqrt, left parentheses 5, right parentheses, press enter. That does the division for us, gives us that standard deviation, which is smaller. And everything else is the same in this problem. So we can leave it alone, and we just take this probability here as our final answer. And not surprisingly, it actually is a higher probability, since it's all getting closer to that center at 10.2. Okay, so a very typical type of problem in this chapter. Make that adjustment to the standard deviation and calculate the probability using that new standard deviation. Okay, now here's just conceptual questions here. So it's asked, what happens to the standard deviation of x bar, that's the sampling distribution, as the number of measurements increases? I'm just going to put it gets smaller. So you're dividing by the square root of n. Dividing by something larger makes it smaller. What happens to the shape of the bell curve? It gets, let me just put skinnier and taller. Centered at the mean itself. Okay, that's a quick one. So here's last one in this section. It says a certain strain of bacteria occurs in all raw milk, and we're going to let X be the bacteria count per milliliter of milk. The health department has found that if it's not contaminated, it's a mound-shaped symmetric distribution. So not specifically normal, but mound-shaped symmetric. The mean is 2,500. The standard deviation is 300. And it says in a large commercial dairy, the health inspector takes a random sample or 42 random samples of the milk produced each day. At the end of the day, the bacteria in each count of the 42 samples is averaged to obtain the sample mean bacteria count, which is X bar. So the word samples here, this is like, it's a little bit misleading. Samples as in they're taking a pipette and gathering some milk, and then probably putting it on a petri dish and letting it grow, and then counting the bacteria at the end of the day just to see if it's contaminated or not. So if we assume that the milk is not contaminated, what is the distribution of X bar? Well, we should really kind of check the conditions just to make sure everything is all right. We remember from the last video, we need random sampling. So it says random sample, which is good. It's this one here. The normal criterion, if the original is normal, it's already normal. And then this, it's not originally normal in this case. So we have to check that the sample size is large enough. So mound-shaped symmetric isn't quite enough for normal, but our sample size is 42. That's over 30, which is good. So we're good to go on that one. And then the last one, it's not really explicitly given in this one, this independent sampling criteria. There's 42. We can estimate. We'd say like, okay, they're using a 1 milliliter pipette and they're pulling some milk out. So that'd just be 42 milliliters. That's not very much. That's not a large amount of milk. It says a large commercial dairy. So we would assume that this is less than 5% of the total amount of milk that they're producing. So yes, it meets all those criteria. And so it does follow or have those properties of the sampling distribution for the sample mean. We can say it's normal, or let's say approximately normal. Sufficiently normal, you sometimes hear. Approximately is a good way to describe it. And I'm going to just say with a mean. I'm going to put the symbols here just in case forgotten. That's what that symbol is. Actually, let me put this over here. Mean of the original 2500. And that's the symbols. And standard deviation. Of take the 300 divide by the square root of the sample size 42, and I'll fill that in a little bit later. The symbols here. Yes. Okay, so let me just put this in a calculator quick. Could do this in Excel if you wanted. Wait, 46.291. Okay, good. Now, assuming the milk is not contaminated, what's the probability that the average bacteria or mean bacteria count X bar for one day is between 2350 and 2650 bacteria per milliliter? Okay, so this is giving us our limits, those two limits, and we're going to use this mean and the standard deviation and get our probability. So here, typing in 2500, and I'm going to do the formula in here just so it's as exact as possible. One thing that you want to try to avoid is rounding before the final answer. And if you type in this formula here, the equals 300 / SQRT left parentheses 42 right parentheses, it'll keep as many digits as it possibly can. You put that in there. Now, our limits we got to put in as well, 2350 up to 2650. And we get a very large probability. So 0.99880,625, almost 100%. Very high probability. So let me just show you what I wrote.